Thank you, Jacob, and thank you for allowing me to speak here. I am going to talk about a project that I have just started, which is computing some invariants. My interest is to compute some invariants which are called skeletons. These invariants are associated to an analytification of an algebraic variety, and more general, they are associated to an analytic space in the sense of Berkovich. And they are very rich. They touch several branches of mathematics. So far, we have just studied them from a combinatorial point of view because they are very difficult to get, very difficult to obtain. And my contribution is somehow realizing that tropical algebraic geometry can be used to compute what we don't know about these invariants. And at the end of the day, we will be analyzing some generalized ramified covering between polytopic spaces. That's the goal. So for me, a variety, unfortunately, I have to work with schemes. So this is not, this is a restriction imposed by the theory because we need the generic points. So it is not my personal option. And I will denote K bar, the category of algebraic varieties. If you don't know what a scheme is, you can just think about it as if you are manifold-like thinker, like a big ringed space, locally isomorphic to some basic object that's called the affine scheme associated to a particular ring, which is a finitely generated K domain without nilpotence and without multiple components. Everything works fine. So why we need to work with schemes is because we need non-closed points. These non-closed points are the points which will be deformed under Berkovich theory. Somehow closed points receive a new name in Berkovich theory, which is called rigid. And they are rigid because they cannot be deformed. Generic points may be deformed, and these are going to be the guys which are going to fill the gaps in this theory. So if you want a concrete example, you can think about the affine line. So the affine line is it's not just the K points or the points of your field with a Zariski topology. It has another point which is called generic point associated to the zero ideal, and this point is not a nice point in the sense of classical topology because it is a dense point. Its closure is a whole line. And this behavior repeats in some other example. And let me describe you what are going to be my fields of interest. I will call a Banach field a complete metric field, but the metric has to be induced by an absolute value. An absolute value, which is an object that is very near from us. It is not an exotic definition. And what is more interesting is that we have several examples there. We have, for example, the classical. For me, whenever I say classical in this talk, I will refer to the classical Archimedean value of the reals and the complex numbers. But we have other examples, for example, the p-adic numbers. To the left side, I am putting the field, and to the right side, I am putting its algebraic closure. I have also the t-adic real numbers, which are just a completion of the field of rational functions over the reals with respect to some t-adic valuation. And to the right, you have the algebraic closures. Just add -1, square root of -1, and you have the concrete description of this field. There is a mistake there. There should be n plus or equal to 1. But this construction may be performed for other fields, but in positive characteristics you cannot give this explicit description of the algebraic closure of these theoretic fields. Also, you have the perfectoids. The perfectoids are some fields in which interest very much the arithmetical people, and you can see it as the completion of the perfection of the p-adics, adding just nth roots of p, and you have an operation which is the flat that translates somehow characteristic 0 to positive characteristic. You have the trivial or discrete absolute value. You just say this is the trivial metric, the discrete metric. This is also non-Archimedean, and I'm not quite sure if the hyperreal numbers, which were discussed on Monday by Professor Ernesto Lupercio, are one example of these guys. I don't know if there is an ultrametric value which gives you the topology of the hyperreal, so question mark there. So this world is very rich. There are several examples of non-Archimedean fields, and what I want to do is analytic geometry in the sense of classical analytic geometry over no matter which one of these fields. Because the theory that we have for holomorphic functions is really beautiful and very appealing to the human mind, but there is a small problem. The problem is that if you happen to work with one of these fields which is not the complex numbers or the real numbers, then the topology is not so good. The topology is totally disconnected. The metric topology of any field which is not the complex numbers totally disconnected, so you may think that you get a Cantor set like metric space, and these are called non-Archimedean. However, this is not a big deal. Mathematicians do not stop at these kind of problems. The first attempt to continue doing analytic geometry over these non-so-good topological spaces was made by John Tate around 60s. He invented some gadget called the rigid analytic space, because at that time Grothendieck was working with toposes, topoi or toposes, and Grothendieck topologies to be able to do cohomologic theory over more general settings, not necessarily over topological spaces. So the problem with this approach is that a site is not really a topological space. You don't have points, you just have good covers, and you can do some geometry there, but if you are a classical mathematician, you don't have points. So this was a problem, but nevertheless, we were able to do shift cohomology, and the idea of skeleton that I'm interested in was already present in rigid analytic spaces by the works of Tate himself. He worked on the uniformization of elliptic curves, analytic uniformization of elliptic curves over the p-adics. And David Mumford worked with an uniformization of abelian varieties and curves in general. Then around the 90s, Vladimir Berkovich introduced a general theory of analytic spaces over any Banach field. So he was able to construct a category of KV analytic spaces which unifies degenerate cases such as the classical or the trivial discrete. If you exclude these two particular cases, everything else is like on the same box. Everything else you can make a systematic development of any non-Archimedean field which is not the holomorphic or the Archimedean or the trivial or discrete valuation. But what is really striking is that Berkovich's theory recovers holomorphic analytification. So let me talk about Berkovich analytification. So I will not talk about analytic spaces in general. I'm just going to talk about some subcategory which is called good analytic spaces, because my Gaga functor will land there. And I will give you the explicit description of the analytification of a scheme as a fibration, quotation marks, over my scheme. So this is my goal. So I was telling you that in general, what prevents mathematicians to do Berkovich analytic spaces is that the theory is extremely difficult. If you follow a course in analytic geometry, like classical analytic geometry by Berkovich, it is it really demands a lot of you, because you need to learn affinoid algebras, you need to learn a lot of things before you can do geometry, before you can jump into action. And this is not so compatible with our times. We don't have time to learn things. We just need to get the idea and get to work. So unfortunately, if you read Berkovich articles or people like do this, they are extremely difficult, they are extremely hard to read, they are extremely general. They don't care to explain the world what they are doing. They are just worried about to get the most general result about excellent or Japanese or catenary rings, and this in the real world makes no sense for me. So at least for me. So let me tell you that there is a subcategory which is called good analytic space. This subcategory is good because the objects in the category are true locally ringed spaces. So you have a topological space with a true topology, you have a sheaf of rings, which is a true sheaf of rings, and we are happy because this setting is more near to the things we do classically. But more important is that there is a Gaga functor which takes an algebraic variety and gives you an analytic space, one of these guys. And this space is called the Berkovich analytification with respect to non-Archimedean valuation, and the properties of this functor are the ones that you expect. If you have ever followed a course in complex variable or in algebraic geometry, complex algebraic geometry, you know what are the properties of the functor. The functor is really nice. It is really a translation between the two categories, the algebraic and the analytic. So the properties of this functor are preserved over no matter which field. And the point is that one can do analytic geometry over honest topological spaces, and these constructions have proved to have links with other branches of mathematics which are very active right now. For example, singularity theory or model theory or logarithmic algebraic geometry, and also tropical geometry, of course. So right now, in my opinion, we are experiencing a new golden age of analytic geometry, because we are trying to get any concept that has proven to be valuable in complex or in holomorphic setting. We are trying to reformulate it to be able to define it over non-Archimedean settings. So far, the community has been possible. It has had some success trying to define a non-Archimedean analogs of minor vibrations or knots associated to a singularity or other kind of things. So how does this work? Well, I must say that when I started to study this theory, we didn't have this kind of technology. You had to read the book of Berkovich, the red book, and there analytification was just a representable functor. So it was really hard to say which was the correct or the actual explanation or the actual object which gives you this construction. But now we have technology more accessible for the youngs or for young people or for newcomers. And we have a really nice description of the analytification, which it's clear that it uses generic points. So the analytification is just the space of pairs. You take an irreducible subvariety of your scheme, and then you take some special functions which go from the residue field of your variety, of your subvariety. This, of course, exists because this is irreducible. So you just take some special functions which commutes with the information that you already have in your field. Remember that your field comes equipped with this data, and then you just complete the triangle by asking some commutativity here. So here, as I say, ky is the residue field of y, and w is just a multiplicative semi-evaluation. This is just an absolute value which departs from your field, and you allow it to have a kernel in the ring of which this is the fraction field. So you have a projection, since you are considering generic points here secretly. You have a projection to the scheme, sending a pair to the generic point of your variety, and this projection is going to induce the topology here. So you just ask the topology to be what you want. You want compatibility with Zariski topology, and you want compatibility with evaluation of functions, which is this. All these functions lands here, and you just pull back the topology of R of this ray. So in some sense, these two conditions are the ones that give this analytification their awesome properties.
But what happens if you take y as 1 point sense? It's not enough. Or...
Yes, let me explain that here. So this framework works in general. You don't need any assumption on the field. You don't need any assumption on the residue ring, nothing. But to make things easier, let me suppose that the field is algebraically closed and the evaluation is non-trivial. Then in some sense, in this case, the set of closed points, that's to say, if you happen to take here an irreducible variety, which is a point, then what happens is that the residue field is an algebraic extension of your base field, which is algebraically closed. So you don't have deformations of the evaluation. You just fill this gap with k here and equal here. So that's why they receive the name of rigid points. These points don't move. These points insert themselves in the analytification, and they don't move. But the generic points, they admit deformations, and there is this vibration, which is a surjective continuous projection of the analytification, which now is a topological space. You send a generic point, comma, the evaluation to the, you send the subvariety to the subvariety here. You cover all this set. This set is as a set, is the disjoint union of the closed points and generic points. And you say that the closed points don't move. So you just need to see what happens over the generic points, over the points which are not closed here, which one is the fiber. And here we have an example. Suppose that you have an irreducible algebraic curve. Then by definition, the generic point is just 1 point. So to really know this guy, you just need to see what happens over this point. And by definition, the residue field of this point is just the field of fractions, field of functions, of rational functions of your variety. So you are filling up the space with pairs, which is the generic point, together with this valuation. And if you ever have seen a picture of a Berkovich space over a non-trivially valued field, this is like what is between the boundaries. So you have here, for example, have here the closed points, and then you have here the scheme. Here there is a projection, and you have an inclusion, and this inclusion is a metric inclusion. So what you just have here is an additional point, which is called eta x. And what Berkovich does is just start with your point and start filling the gap, like this. And this is continuous if you put here the Berkovich topology, and here you put Zariski topology. So this process fills the gaps, and some geometry happens here. And the point of skeletons is to erase the unnecessary information that this process gives you here. So this process gives you a lot of information which is not relevant to the geometry of your variety. And the theory of skeletons tells you which part is relevant for the geometry of the variety. So, thank you. So, as I say here, in general, these spaces are very big. These are valuation spaces. And we need tools to better understand their properties. So, let me introduce the concept of a skeleton. But I need some technical tools. Every non-Archimedean field has two things attached to it. It has a valuation ring, which is the unit ball. And a residue field, this guy is a local ring, so you can take the quotient by the maximal ideal, and this guy is a field, and you have this diagram. This diagram is very frequently used in classical algebraic geometry when you want to do some kind of deformation theory, but over schemes of dimension 1. So for simplicity, let me suppose that the residue field has characteristic 0. The reason behind this is that secretly I will use a semi-stable reduction theorem, which basically relies on Hironaka's theorem on characteristic 0. I'm not still updated on the status of Hironaka's works for characteristic P, resolution of singularities of characteristic P. So we just need to use the case which has been proved for sure. So what is a skeleton? A skeleton, if it exists, so this is a big if. I'm not sure if every analytic space has a skeleton, but most of them have one, and the problem is finding it. So what is a skeleton? Is just a subspace that sits inside here, which has a structure of finite simplicial complex, and such that the inclusion is a strong deformation retraction. So this gives you, this tells you that the old algebraic topology of your analytification is saved in this guy, but there is more. So it is not just the homotopy type, but also more information is stored in this guy, and as I will tell you in a moment. So it is just some kind of polytope. You can think about this as some kind of polyhedral complex. And everything outside this polyhedral complex is irrelevant. Let me give you an example. If you have a smooth and irreducible variety over a field, the field has to be like this. Then this guy exists. And now, classically, people have been using strongly semi-stable models over the evaluation ring to find it. I will explain it in a moment. So how do you get the combinatorics of the skeleton? You just construct one of these guys over the evaluation ring, then you take the special fiber, you take the dual complex of the intersection of the irreducible components of this guy, and the realization of this complex is homotopy equivalent to the skeleton. So this is to some extent the best you can do with algebraic tools, with classical algebraic tools. Everybody that in some sense has been dealing with this kind of ideas uses this path because this path is well established. And the problem with the Berkovich definition, original definition in his articles, is that he used very, very heavy machinery because he's interested in arbitrary characteristics. So if you happen to be interested in singularities over positive characteristic or other problems, more complicated problems, maybe you will need to use de Jong alterations or plurisemi-stable models, which are some étale morphisms for formal schemes. So the theory is really, really difficult, and mortals frequently rely on this theory, which is more algebraic and more accessible to common people. So just the idea is that a model is it's a generalization of a Néron model. A Néron model is just something that gives you arithmetic information of a scheme out of the reduction and the generic fiber. So it's just, you just see a scheme over evaluation ring as a pair of something which is over the residue field and something which is over the quotient field. So this guy glues together two fibers, and there is a transfer map between one of them and the other. And this guy has to be semi-stable in the sense that you don't allow singularities which are worse than double points. Here you just allow some very well-controlled singularities, and this theory is really, really powerful to learn the geometry of these schemes. You may do it by controlling these kind of fibers. So in order to get this kind of fibers, frequently you have to desingularize. You have to do blow-ups, and this is why this works fine in characteristic 0, but in positive characteristic we're not so sure. And the dual complex is the thing that you're thinking about. You just keep the intersection profile over these divisors, over these singular, non-singular fibers, components, and the intersection in information of these guys is going to give you the dual complex. So now, thank you. For simplicity, let me suppose that my guy is smooth, irreducible, and proper, so that I can ensure that the skeleton exists. And let me give you an example of this, how this works. But this is in some sense a stupid example because it works over F1. I mean, it will work over no matter which ring, not just valuation rings. Let me consider the projective space, any projective space. So these guys are algebraic. This is just Pkn. Then I am saying that the skeleton is a point. So there is a subspace here, which is a point. And, sorry. And I am telling you that all this guy retracts to a point. So I'm saying that any analytic projective space is contractible, but I'm saying more than that. I'm saying that any Grassmannian is contractible. And this is what is sad about the field. I was in Brazil in the Satellite Congress of Tropical Geometry and Non-Archimedean Geometry, and I was asking frantically what was the skeleton, the Grassmannian, to the experts, to the leading experts of the field, and nobody knew. So I thought, many people thought that this was a Stasheff associahedron because of the combinatorics resemble a lot to the combinatorics of the Grassmannian. But nobody was sure about the skeleton of the Grassmannian, and I tried to compute it, and I realized that it is just a point. Why? Because you have always a smooth model over F1 for the Grassmannian. Let me give you that model. So R is an arbitrary ring. These are Grassmann-Plücker coordinates. I mean, they are indexed by k subsets of a set of n elements. And here you have Grassmann-Plücker relations. Grassmann-Plücker relations are very combinatoric. They are just like xi plus a, xj minus a from 1 to k plus 1. And here you demand that the cardinality of I is k plus 1, and the cardinality of j is chi minus 1. So the process, the combinatoric process of the Grassmann-Plucker relations are that you start with a k plus 1 and k minus 1, and each time you take away one of the points, one of the marks of the k plus 1, and you add it to the guy which has less. And then you are, sorry, I forgot a sign here. So all the Grassmann-Plucker relations are like this, and look, there is something very important here. The coefficients are minus 1 or plus 1. So these relations are defined over F1. That's to say you can define Grassmannians over no matter which ring because you don't have coefficients. So if you take the evaluation ring of your field, and you take this guy, this is a smooth model for the Grassmannian over no matter which field. And if you reduce this to take the special fiber, nothing happens because there are no coefficients here. So you recover your actual Grassmannian on the residue field. And this says that the reduction of the field of the model to the special fiber is smooth. On the other hand, the skeleton is just the dual complex of this guy, so it's just a point. So, in particular, the projective space, projective line, analytic projective line is contractible. But this is not true in complex the complex world. Complex world, we know that the projective space is not a point. So what is happening? It seems that you are losing information, but that's not the point. The point is that the tropical geometry will recover the information that you are losing topologically. So let me give you another example. You have a smooth projective curve of genus G over K. Then the skeleton is a finite graph with first Betty number at most the genus of the graph of the curve. Once again, it may be the case that we are losing information because I am not recovered the whole first Betty number, which is the genus in some sense. I'm just recovering something which is at most that. So for example, if you have an elliptic curve over K, this may be a finite graph, this is a skeleton with at most one cycle. But it may happen that this is just a tree. And in general, if you increase the genus, this is going to happen. Once again, what I did for the Grassmannian is, in general, it is not easy to do. You need to find a scheme over a ring, not a field. So this is very, very hard because you have to control the arithmetics and the geometry at the same time. And your scheme over the ring must have some properties with respect to the specialization when you quotient by the maximal ideal, or when you extend to the generic fiber. So the point is that this is not very easy to do. You have to learn a lot of algebraic geometry in order to do something. And, well, my point is that this is hard to do, no? And moreover, this process just recovers you the homotopy type of the skeleton. It does not recover the remaining information of your variety. But skeletons in the theory of Berkovich carry more information, and we would like to recover it. Also, skeletons are not unique. Skeletons, once you find one, you can find more, and it is not clear if there is a unique version. But in some cases, it has been proved that these guys are unique. And when they are unique, they are also birational invariants associated to your variety. And this example is called essential skeleton. A lot of big names are working right now on essential skeleton. And by Lefschetz principle, if you are working with a field of characteristic 0, the birational information that you get from non-Archimedean things is going to transfer to the complex setting. So these tools are not just for the non-Archimedean people, they are interesting also for the classical people. Remember, for me, classical is holomorphic. So just let me go to the final part of the talk. It's a connection with tropical geometry. And here I want to say some words in my experience. Berkovich theory is very famous because it is really difficult. But on the other hand, on the other side of the spectrum, when you say to some people, some circles, that you are doing tropical geometry, they think that you are doing child's games, like you are doing metric graphs or piecewise linear objects inside some Rn, and they just don't care about what you do because they think that this is not important. But my point is that the skeletons are the middle point between Berkovich geometry and tropical geometry. So this may interest more people in studying Berkovich because it's not going to be so hard, and this maybe interest more people in doing tropical because it is not going to be very easy. So let me recapitulate. I have a nice Banach field. You can think about the algebraic closure of the Puiseux series over the complex numbers. And I have a nice variety. You can think about a projective smooth variety over this field. And so there is a guy which is called skeleton, which is very nice from a combinatorial point of view, and you have a strong deformation retraction for the whole space to this guy. And the point is to compute this skeleton. So, of course, everything that I have said here would be great if this could be applied to general case. I mean, to any variety which is not embedded in a toric variety. But so far, up to my knowledge, we just have tropicalizations for subvarieties that admit an embedding into a toric variety. Or if your variety happens to have an open set which is embedded in some algebraic torus. So let me suppose that my variety, apart from being nice and defined over a nice field, it has an embedding into a toric variety. The toric variety may be any toric variety. It doesn't have to be proper or non-singular, or it doesn't matter. So the embedding, suppose that you have here a closed embedding. And this gives you a tropicalization map. This guy embeds, at least the closed points, embeds in the analytification. There is some tropical toric variety associated to this. And there is a map which is called tropicalization. I'm going to define it in some minutes. So this tropicalization map has a lot of advantages. For example, the image is just the support of a weighted balanced rational finite polyhedral complex of the same dimension as your scheme. And it lives inside some partial compactification, which I call trop y of Rn. So let me read the description from below to up. Finite polyhedral complex is just that, a set of Rn which has facets and which has some good intersection properties. You can think of it as a polytopic complex if it is compact, or polyhedrons as intersection of half planes. Rational in the sense that all these guys have rational slopes, so they are supported on hyperplanes or on K-planes, planes of the right dimension, which can be defined by equations over the rational numbers. Weighted is that you can put some weight function over the facets. Balance means that it satisfies some Riemann-Hurwitz condition on codimension 1 faces. And support of is that you have a bunch of polyhedrons and you just take the union, and this guy is going to be your tropicalization. So this is a very combinatorial object. For example, maybe you have seen a tropical line. If you happen to have, for example, an equation inside K2, this is a line, and if you, of course, this guy is already a toric variety, so you can tropicalize, and the picture you see is this. So in general, you can think that tropicalizations are these kind of objects. And the problem is that the fibers of this fibration, because this is continuous and this is continuous and surjective over the image, the fibers are extremely difficult to compute or to know, because these are spaces of valuations. And my point is that we don't need them. So when I ask experts about this possible thing, this possible tool to study the skeletons, they told me, but how are you going to describe a section if the fiber is extremely difficult to explore, it's extremely difficult to know? And I said them, well, I don't need a fiber. I just need to assume that a skeleton exists. And then I can compute this section instead of caring about the fibers. And this is my point. You don't need the fibers. So let me tell you how to do this. Since I am in a toric variety, toric varieties comes with a decomposition of toric boundary and the torus. This is K star, some boundary divisors. So this induces me an stratification of X. U is the dense part, the intersection with the dense torus, and D is the boundary divisor. So I have a diagram. The tropicalization will induce a tropicalization on this guy, but the advantage is that U lives inside some torus. So tori admit coordinates. Well, but at the end of the talk, I will say that once I assume that skeleton exists, then I can construct this section, and basically what remains is a projection from here to somewhere here, and this is going to be what I call a generalized ramified covering space, in the sense that it may be ramified over whole open subsets of the base, and it may not be a well-defined global degree, but there are always local degrees which exhibit some Riemann-Hurwitz type phenomena, thanks to the balancing condition of tropical cycles. So this is what I was telling you before. I have coordinates on tori, so I can find an ideal such that the set U is given by solution of I, of the elements in I, and there is some statement which is called fundamental theorem of tropical algebraic geometry, in which you have several descriptions of several objects, like 5 or 6 of them, and the point of the theorem is to say that everything is the same. And 2 of the guys appearing in this theorem are the tropicalization of U coming from the analytification. So just to be clear, there is a map in general. There is a map coming from the analytification to the tropicalization of the toric variety. But U is a subspace, so you have here you have a simplified version, because here you care about boundary strata, here you don't care about boundary strata, so this is more easy to define. And this image lives here. And this guy is not hard to define. You just take points in Rn such that the initial ideal, which is some sort of degeneration using P as weights for your variable 6i, is not a monomial. So let me just, for example, if you take Bx plus y plus 1 inside K2, the image that you see is that you are going to take a point in R2, and then you are going to perform one operation to this polynomial. What I'm saying is that the initial ideal of this polynomial f here is just the monomial y. The initial ideal here of the polynomial is just the monomial 1, and the initial ideal of your polynomial here is just x. And when you don't have a single monomial, once you perform the initial degeneration, that point is going to be in a tropicalization. For example, if you take one point here, what I'm saying is that the initial ideal is comprised by y and 1. So this point by definition is in your tropicalization. And then all the other points that appear are going to have a combination of 2 or 3 of these guys, and they are going to appear in the tropicalization. So this is very convenient because I don't care about analytic geometry no more. This is a very complicated way to do it. You send a point together with evaluation to the logarithm of the evaluation of these coordinate functions on the point. So this is hard to do and difficult, but this is defined over the whole analytification, and this is more intrinsic to the open set. So I am entering to the final part. The thing with this definition is that you can define it to set up a multiplicity function. The multiplicity function, you just take the initial ideal, you quotient your polynomial ring or Lorentz polynomials by this ideal, and then you decompose it as sum of irreducible varieties together with multiplicity. So this is something that happens in algebraic geometry. In algebraic geometry, if there is nilpotence on your sheaf, then there is geometric multiplicity, and you have to count that. And the way to count this is like this: is the length of some module, which is an R10 ring, and this guy is positive and finite, and this gives you the profile, the ramification profile over the facet. This decomposition of M as sum of Mi is what gives you the ramification profile over the particular phase where you are computing this wave function. So at the end of the day, you get a pair, which is called tropical algebraic cycle, which is what I said here. Support of a weighted bands rational finite polyhedral complex of the same dimension as your space. This map is locally constant, so you can use this feature to define to find the rational polyhedral complex that realizes your set as the support. And, well, main feature of these pairs is that they satisfy balancing condition at every codimension one phase. And this is a global generalization of the concept of Minkowski weight. And this is a combinatorial gadget which appear in cohomology ring of toric variety. So just to finish, conclusions, what I'm saying is that so there are a lot of things coming together. You start with a variety, then you analytify it, and then there is one guy which is the skeleton. So somehow you can construct a guy which is trop U, over which this map induced by tropicalization is a generalized ramified covering. This guy is a polyhedral complex. This guy is a polyhedral complex. They both have the same dimension, so the fiber is 0-dimensional. And how are you going to find the ramification profile over a dense phase? It's going to be given by this decomposition in positive integers of your weight function. So this function, for example, is 3. You compute it, and it is 3 over the tropicalization of U. Then you may find 3 different branches projecting here, or maybe you will have one branch of weight 2 and one of weight 1, or maybe you are going to find just one fiber of multiplicity 3. And this is perfectly valid. You can have an open set here such that everything is glued. So there is no codimension 1 set over which things are étal or over which things are nice. This can happen. And the final point is that not only you get the combinatorics, so you just don't get the topology or the combinatorics of this guy as a ramified covering over this guy. You can use initial ideals to compute models, and you can use the fact that you are working on inside Rn to see the affine structure. This is inside Rn. As I told you, every phase here is inside some rational k-space, linear k-space. So there is a lattice here associated to your phase, and this is basically the logarithm. So the logarithm has an inverse, which is exponential, and you can pull back the lattice that you get from tropical geometry to your skeleton. So this is an enrichment of the combinatorics of the skeleton. You can also get the models of the skeleton using initial ideals, and this gives you more information about this object, more than just the combinatorics. So let me finish with my example of the elliptic curve. What happens? I have here an elliptic curve. So maybe you have the skeleton is just a circle, or maybe it is a point together with some branches. This happens if the B1 of your skeleton is 0, B1, the skeleton is 1. So how do you recover tropically the information that's lost here? There is topological information lost here because you don't get the genus of your curve. You recover it by looking at the initial ideal here. If you have an elliptic curve inside P2, so this is going to be some point inside R2. You perform, this is a hypersurface. If you perform the initial ideal at this particular point, branching point of your polynomial, and you take the quotient by this. This is going to give you an elliptic curve over the residue field. So by model, I mean that you have here an elliptic curve living in the residue field of the particular point. So there is no loss of information. Even you can recover it topologically, or you can recover it algebraically by looking at the model. And the tropical world recovers it for you as some initial degeneration. I think that's all. Thank you.